Welcome everyone again. It is now a couple of minutes past the hour, so in the interest of time, we should start. Our virtual workshop on reference materials supporting characterization of nanomaterials, current status and future trends is organized as part of the ConcenSus project, which is focused on establishing traceable concentration measurements of particles for more sustainable industry. My name is Dorota Barczak, and I'm the coordinator of this project and science area leader for particle characterization at the National Measurement Laboratory in the United Kingdom, hosted at LGC. I have here today with me my colleague Guillermo, who will help us to moderate this event. And I also welcome Dan Hodoraba from BAM, who is part of the organization committee of this workshop. Before we start with the scientific part, I would like to mention few of the housekeeping information. All attendees are automatically muted, but you are more than welcome to keep your cameras on. We should have enough bandwidth to accommodate that. If you have any questions to our speakers, please post them in the chat. We don't have the Q&A functionality enabled. We will be using chat in this event. At the end of the workshop, we'll have an interactive session that will involve participation of you all. This session will be held using Slido, but there is no need to install this app, don't worry. All questions will appear in the chat once the session starts, and you will be able to vote directly in the chat. You won't see all questions at once, only the question that is enabled. There will be 3 questions in total. The whole event is being recorded, and the recordings will be made available to all registered participants at the end of the event. With that, I would like to move on straight to the agenda and hand over to my colleague Dan, who will introduce you to the technical part of the workshop.
Thank you, Dorota, and a warm welcome from my side. I am Dan Hodorova, representing BAM and the same project, ConcenSus, together with Dorota. And we have selected 4 talks today. The first one by Håkan Emteborg from JRC on particle in suspension from atmospheric dust to microplastic. Let's see, Håkan, how far we come with the slides. Then we have David Ojeda from LGC on SI traceable characterization of the first reference material for nanoparticle number concentration. We have Vikram Kestens again from JRC. He will join us a little bit later, and I am sure he will do this when he promises it, about accurate size measurement of nanomaterial constituent particles using 2 new certified reference materials. We will see exactly which of them when Vikram will join us. And we have my colleague from BAM, Andreas Thünemann, with the topic on development of nanoplastics reference materials in our institute. And as said, at the end, we have the last 25 minutes in form of this interactive session and panel discussion. I wish you and us good luck. And let's start first with Håkan. And exactly. And then the sharing has worked already. If you activate the presentation mode,
yes,
should be directly the right one. But we know how it's work.
Is this okay, or should
yes. No, please do it. Yeah, swap presenter.
Okay, like that.
Yes, thank you.
Now it's full screen. Okay, welcome everyone. My name is Håkan Emteborg. I'm from the Joint Research Center in the reference material unit, and I have worked here a couple of decades in the processing and production of certified reference materials, and the JRC is one of the major matrix reference material producers in the world. And I'm here to try to provide an aerial shot. So perhaps some of the things you will hear are self-evident for you, but I take this from the point of view of a reference material producer and also intimately linked to why the metrological traceability is so important for our activity. So we will see, like it was said, maybe I don't have time to go through the atmospheric dust, but you will see one or two examples of the microplastics works we've been doing here. So I will start with the meter convention in 1875, and before that, the French Revolution introduced these new measurements like the litre, le gramme, le mètre, and these units then percolated through society. So in 1875, it was the time to establish by a number of signatories the meter convention, which later translated into the SI system in 1960, where you see all these base unit that we now are so used to in our working environment. So most of the time when it comes to the certified reference materials, we express our SI traceable units based as mass fractions. So it's basically going back to the kilogram, and traceability is all about, in fact, about comparability of the measurement results, which are indeed very important. There is a famous example from the end of the 90s which was actually caused by a traceability problem, because there was that NASA climate orbiter was lost because the same numbers, the same digits were used on both sides of the Atlantic, but on one side of the Atlantic these numbers were in imperial units, and on the other side of the Atlantic in Europe it was in the metric units, and it ended up the scientists on both sides used the same numbers, as I said, but different reference points, and in the end that orbiter crashed on Mars. So the definition of metrological traceability is a property of a measurement results whereby the result can be related to a reference through an documented unbroken chain of calibrations, each contributing to the measurement uncertainty. I'm sure most of you know this. For a reference material producer, we are dealing with, especially here in the Joint Research Center, we're dealing with limit values in the European legislation. And here I have an example of a certified reference material for regulated heavy metals and other elements in drinking water. And there, as I say to the visitors that come and see us, what we actually produce here is truth in a bottle. And you receive a material and you receive a certificate. On these certificates, the truth is stated. And I will go through the example of lead here, but basically the use of certified reference materials in analytical laboratories all over the world is they work as traffic lights. If the laboratory is unable to remeasure the certified reference material and find the certified value, the result is wrong, and they have to go back to root cause analysis, what is going on in their laboratory, to make sure that everything is correct. It's a good way to show that your measurement process is under control. So in the European law, we have, as of 2036, the value for lead in drinking water should be 5 microgram per liter. Until that point, it's 10 microgram per liter. The reference material, the example I have here for the measurand, the mass fraction of lead in drinking water is at this point then formulated as 10 microgram per liter. And if you show this graphically, you have the certified value and have the current certified reference materials. It's fit for purpose also in the future, where it will be slightly above the legal limit. At this point, it's slightly below the legal limit for the drinking water in the EU. So why do I go on about this? Well, you look at the certificate, you realize that the gram is mentioned in the unit. This is where the metrological traceability comes from, whereby people can compare their results. So this is indeed very important, and I will say a few words about the traceability statement themselves later, because they're actually mentioned in the footnotes there. It's perhaps a little bit difficult to see, but it's actually saying that the certified values and their uncertainties are traceable to the International System of Units, SI. So indeed, for a trueness test in your laboratory, you need a certified reference material or spike recoveries. And there, as indicated, the microgram per liter. What is very interesting with this certified reference material is the characterization exercise, because when we certify a material, we're interested in having as many possible techniques as possible for the characterization. And here we see that for the characterization and to come to the unweighted mean of those results, it's very advantageous if you can use different detection principles for the actual quantification of lead when you do the certification or characterization exercise. So you can see on the x-axis you have quadrupole MS, ICP-MS, you have electrothermal atomic absorption spectrometry, anodic stripping voltammetry, you have again ICP-QMS, and you have a sector field ICP-MS, and again atomic absorption. This is a beautiful example of different detection principles used for a quantification of the same property or same measurand. Unfortunately, I don't think we will be able to reproduce this material in the future, because it will be difficult to find laboratories nowadays that are operating atomic absorption and electrochemical methods for this. So this is a way I give this example. It's maybe not only useful if you only use one technique for characterization, because it narrows down your traceability statement actually. So the conclusions I want to make on this traceability part here, that metrological traceability of the measurement results is of tremendous importance. You remember that Mars orbiter that was lost there. And if you are an RM user, you should look for the traceability statements on the certificate of analysis and apply them in your 17 or 25 accredited environment, because the third-party assessor will ask you how you can verify and demonstrate you have achieved metrological traceability for your measurement results. And if you use certified reference material from a competent producer, you're able to show this. And if you are an RM producer, you make your best effort to provide a clear traceability statements. And understand the limits of your traceability statements. That means that if this connected with the techniques used for the characterization and the definition of the measurand, if you're an RM producer. And indeed, the metrological traceability can be demonstrated through the use of CRMs from competent RM producers, and particularly important for matrix materials. So you can look in ISO 17025, clause 652 and Annex A3 there, where it's described how the metrological traceability can be guaranteed through use of CRMs, and what is considered to be, which entities are considered to be competent RM producers. Now we'll go in a little bit more detail about the certified reference materials, the processing production part. So certified reference materials are reference materials of the highest possible quality. These are tools for dispute resolutions in court cases actually. They allow for trueness checks. As I said before, they provide the metrological traceability of the measurement results in the specific matrix, and they are anchor points for analytical quality assurance and quality control in laboratories. That's all very good, but there is a limited supply and availability of certified parameters for a wide range of analyte matrix combinations. There's a long time to market for new developments, and there's a lack of flexibility and poorly adapted to new fields of measurements and non-targeted analysis. So CRMs are non-existent for supporting urgent measurement needs in new fields of measurements. That is unfortunately the case. And as a certified reference materials or a reference material producer, we are operating under accreditation under 17034, and also the measurements that go into our materials, they are under 17025 in accordance with 17025 accreditation. So we can look at the measurements in this picture. This I got from a journal. You see the reference down there. It's not my invention, but So these authors, they claim there are 5 agents in a measurement process: the measurand, the method, the standard measurement units, which would then be your unit to which you're traceable to, the instrument and the operator. But I would like to add the sample, also the material, or maybe it's a characteristic of the current practice to actually lose focus on the sample, because we're so focused on defining the measurand and which methods to use and all that we actually halfway forget about the sample. And since I am in the material processing, we deal with sample and matrix materials all day, but I can illustrate this in a different way also. So the analytical quality assurance accreditation 17/25 for the validation, verification, and validity of results, this analytic quality assurance, you can achieve that through the use of reference materials, which indeed are materials. You do this in a proficiency testing round, or you have a validated standard method through ISO and CEN, but the proficiency testing is relying on a material that is circulating between the labs, as well as for the external method validation of a new standard method of ISO and CEN also needs a material to be sent around. So the materials are indeed very, very important for the measurement process. It goes without saying, but perhaps the current practice, especially among metrologists, analytical chemists, that you lose a bit focus on the sample. So I call this the 3 amigos of AQA: reference materials, proficiency testing, and validated standard methods. Now reflect on a method-centric versus a material-centric vantage points for new measurement challenges. This is really a problem, and we have illustrated this in the following way, because when you prepare a reference material, you need accurate and validated methods to produce CRMs, while the CRMs are used to validate methods. So this hen and egg problem, which was first. So in fact, in emerging fields, both RMs and reliable methods tend to be missing. What do you do? So we formulated this circular argument here in a way. We call it the RM/method causality dilemma. And this is actually for characterization based on interlaboratory comparisons when you certify when you characterize your reference material, actually, to certify values in there. We described this in these publications back in 23. You will actually see that it actually coincides a little bit with the title of my talk here. So that paper is called Paving the Way for New and Challenging Matrix Reference Materials, the Particle Suspensions at the Core of Material Processing. But working on that, we formulated this dilemma and what it actually entails for the RM producer. We need good methods out there, but those who develop method needs good reference material to be able to validate their methods. So that's indeed a dilemma. And this is partially the culprit for the long time to market for new CRM developments. This built-in conflict between the access to methods and access to good materials. This was not really new, because Steve Weiss proposed originally in 22 here the concept of providing common samples for a community of researchers may be the future in the development of CRMs. And we described in the paper I just referred to, we suggest that a reporting interface for analytical results should be coupled with such a pool of common samples where anonymized measurements result would be publicly available for all. And now I come into I also described this in the editorial for the topical collection in ABC from last year, that how the respective communities should address these challenges in the best way for future RM developments, preferably working together. So in fact, that the ISO 17025 is a normative reference in ISO 17034 is actually not such a big surprise, because it's the method and the material. So it's the two sides of the same coin. So indeed, the analytical method used for production of RM should be in accordance with 17025 as a minimum, if not accredited. So it's actually alludes a little bit to this problem, even though it's not clearly spelled out. If I now describe this in practical terms, when we prepared reference material for microplastics, if it's a mass-based approach for microplastics, it could be prepared in the following way. So if you prepare a lead standard, you would dissolve lead in nitric acid perhaps, and you will come to a certificate with a very low uncertainty. That's an example from a NIST material, but for microplastics, we then cryo-milled polyethylene terephthalate. We adapted the particle size distribution, and we have a suspension of continuously mixed sodium chloride solution where these PET particles are suspended, and from that suspension we are continuously aliquoting by pipetting from that suspension. And could you prepare, let's say, a PET calibrant or a PET reference material rather in this fashion? And this was what we started quite a number of years ago. The question is how reproducibly and how well could you actually do this? There's no risk that you will be as good as for the lead example, but is it usable? So I show again this suspension here, 10% sodium chloride. We prepare actually out of that a salt cake because that suspension with the PET particles embedded into it is freeze-dried, so the microplastic particles are immobilized in the salt cake. And we prepare a surfactant that we provide to the customers and a bottle with water. And then the whole idea is that the microplastic particles are rinsed out of those vials into the bottle of water using the surfactant, and you have your ready-to-use reference material for a certain number of microplastic particles per liter, or a quantity, in that case, microgram per liter of microplastic particles. So this is the way it looked in the production. We prepared 700 units of these materials. So we had to fill 700 bottles with water. We had to prepare 700 salt cakes and 700 surfactants. But this just shows a little bit the production situation of that material. Now I come back to this RM method causality dilemma, because when we evaluated those first attempts of preparing the salt cake, we had only access to a home, let's say not homemade, but home devised method using ultra micro balances, where we actually weighed the amount of microplastic particles that was embedded in these salt cakes. And there, using that technology, we found a between bottle heterogeneity of 14%. So that was a rather rudimentary method, but that was the only thing we had available for fast checking in-house. So that's why I put that circle of the RM method causality dilemma there. Later on, we devised a QNMR method where we, with a better method, we could actually prove that the same material had an even lower between bottle heterogeneity than we actually envisaged or understood from the beginning, just because we had access to a better method. And nowadays we have access to an even better method, but I will not go ahead of that. We want to publish that before I show those results here. So indeed, it's the same reference material, the same salt cake, but the better homogeneity than initially established thanks to an improved method, incremental steps of improvement, and this is what it's all about. So this is indeed the material that has resulted out of that. This is for sale since February 2025. It's not a fantastic material, but it's the first reference material for microplastics that we have for sale right now. And I want to show this, that here is the RM production information sheet. Product information sheet, sorry. So it's somewhere between 300 and 500 particles per liter of a specific particle size range, and somewhere around 400 microgram per liter of PET plastics. And you have to realize that reference materials are products that evolve thanks to improved material preparation and improved analytical methods. So it's just like cars, in fact. So I think we have prepared here a T-Ford, and we are looking at improving this shortly, making it maybe into a Beetle or even something more modern than that. But indeed, that's the whole, and that's why people say to us, "Oh, we need a certified reference material," but we can't produce a really good certified reference materials unless there's a good methods out there. So this is how a little bit from a reference material producer's perspective, how the things fit together. So I will now go into these common materials, the supply of common samples that Steve Weiss formulated in 22. So this is an idea we have been sketching a little bit, and I gave this talk at the BERM conference last year in Canada, where we thinking of producing about 1,000 units of a matrix, a common material, We know the bulk homogeneity, particle size, and water content. It would be a symbolic price tag. We will take care of storage and distribution, and there will be an analytical results database for this material as I formulated before. So we have we have the material processing, we have the storage and distribution, but we don't have that database. So the initial approach for such common materials could be, as I said, different matrix presentations here, dry powders, heat sterilized pastes, acidified gamma radiated water, other liquids, fresh frozen homogenates. Imagine we prepare about 1,000 units of each such common material, or like NIST is calling them, the research grade test materials, the RGTM. We could have 10 matrices of water, sediments, materials from the AOSC food triangle, food that matches environmental samples, so on and so forth, PM10, PM2.5 powders, and so on. And then we store these at -20 without really knowing what is the optimal storage conditions for all the parameters in there, but that's a good starting point. And then we ship on cooling elements to labs who wants to measure whatever they want in these materials. This is a common approach to this Bowen scale from the 60s, which one of the first matrix materials that was out there. But if you follow Bowen's classification of analytical results, one could apply other criteria for the data pools here, but the size of the circles in this common material indicates the number of results or a pool of laboratories, and the different colors indicate the different parameters. So the mass fraction of cadmium or permethrin or whatever. And so the larger the circle is, you could say something about in this common material, we have of the green parameter, the light green parameter, we could say something like a recommended value. We have 10 laboratory means using more than one technique, and the mean values, there is exclusion criteria for excluding outliers and so on. But anyway, you generate a pool of results on these universally accessible materials, and the only thing we need here is a good database to report such results into. So this is something that is on the drawing board here at the JRC, and let's see if we can develop this further, that it will be actually a resource or a service that would be available in the future. So I'd say that, yes.
Apologies, couple of minutes warning.
Good. So I will have to skip the dust, but that's fine. Coming to the end with these common materials here. So I'd say the common materials are the research grade test materials. The main beneficiaries are RM producers and PTF providers. Their pros would be faster access to a network of laboratories that are capable of specific measurements. The cons for us would be that the stability and homogeneity of target parameters that are not assessed and must still be evaluated as a second step of such a process. And research laboratories, analytical method development, and standard bodies, they could also draw useful conclusion based on the data, because they will have a means of comparable, they can compare their measurement results, since the same matrix is used over a number of laboratories that make use of these common materials. So there is this looking ahead, what we invested for the future of these kind of materials. They could serve new development, solving the dilemma. So indeed, in '64, we had the Bowen scale that was not certified for anything, but a lot of people were measuring elements in that. We have here in the mid picture the certified reference materials that are extremely targeted for the certified values. If you consider in the future the common materials for non-targeted analysis, we could actually envisage a little bit going back to Bowen's, back to Bowen scale, what's that BTB is standing for. So the conclusions here is that the current approach to RM production is possibly too method or technique centric. The capabilities of analytical chemistry in general has expanded tremendously during the last decades, and the current time to market for new matrix CRMs is too long. So we think it's partially caused by this RM method causality dilemma, because we really need access to good methods to be able to certify, especially for new fields of measurements. A way of solving this, that the future RM production should be more material matrix centric, and we could introduce a set of common samples as common materials, or RGTMs as outlined here, would support ARM producers, PT providers, laboratories, and standardization bodies alike with different aspects of their work. And many ARM producers have the necessary building blocks for common material provision, except for anonymized public database for reporting. And that's the end. I stop here because I will not have time to go through this atmospheric dust material. So I stop there, and I thank you for your attention.
And thank you so much, Hakan, for the good overview. And we have proposed and asked in the chat to collect some questions. Until now, no questions. No question. Do you have, maybe let's take one question and looking at the time from the participants. Please raise your hand. Because otherwise, maybe I can break the ice, and we have seen almost on each slide the reference material and developments and advantages, disadvantages. What do we do for cases where we don't have a reference material, where maybe it's not possible? Does the modeling help? In some cases, yeah, X-ray spectra results can be modeled physically quite well. Is this an alternative?
Yeah, that's difficult to answer. We are so focused on matrix reference materials, and any matrix will result in different interferences and background. So to isolate just the spectrum by itself, it is yeah, that's not really possible without the matrix present. So I'm not so familiar with that, what you're actually, how that would work in practice. I do think we are there is a tremendous focus on the actual measurement themselves, and less, as I've tried to outline, less focus on access to a good number of initially, let's say, rudimentary characterized matrices that many labs could use simultaneously and measure different things on.
Okay, thank you. And maybe let's do for the democracy reason here. Let's take the question from Noro, Johanna. I hope it was right how I have pronounced the name. In the case of common material, what would be the difference between a JRC provided material and a material provided by any reference material producer or PT organizer? Until now, the difference is about the certification plus preparation and SI traceability. You can read it by yourself.
Yeah, I read it.
Sorry.
I had a slide which I did not, which I deleted actually from that deck, and that's where I proposed that this model can be used by a network of producers. So it doesn't have to come from the JRC, as it doesn't give it a certain status at all. It's just that the provider of the material will have to demonstrate that the matrix is sufficiently stable, and there it has some basic parameters like that it's known that it's universally, the particle size distribution of the material is universal over the whole batch that is produced, for example. Then when it comes to the certified reference materials and the values that are metrological traceable in those certified reference materials, that would be an end product of a common material. A common material would never at the outset have a certified value. At the beginning, it's a bottle, and it's distributed, and everyone can measure what they like in that. With time, hopefully, when you populate the database with results, you would be able to obtain results then from that database, where perhaps 10 laboratories have measured targeted the same measure round in that, and that could be a starting point for certifying parameters in such a material. That would at least give us, the producer, access to a network of laboratories, which is sometimes very difficult, especially in new and emerging fields.
Okay, thank you so much, Hakan. And
You're welcome.
we would have a second question, good question. And what about transport? I propose that Dorot, I think you agree, and David is waiting. Maybe Hakan, please, you can answer in the chat, and we go to the next speaker, to David. And he will present us SI traceable characterization of the first reference material for nanoparticle number concentration. Please, David.
Okay, sorry, I'm still sharing the screen. So hopefully you can see it. And yeah, thank you, Dan. So this talk summarizes the story of a methodology that we developed within the NML. And it's an SI traceable methodology for number concentration for nanomaterials. And the talk is going to be about a bit explaining the principle of this methodology, also to show the performance of this method for different nanomaterials, and also to go through the verification of this methodology to different intercomparison levels. This all will lead to the final production and characterization of the first reference material in particle number concentration. And we can conclude with some remarks on why this information or this type of materials are so important, and mostly for to support the regulatory compliance. Okay, as a quick introduction, just to mention that nanotechnology is growing in importance every day. And this is something that we can see not only from a financial perspective, but also based on the number of areas that are influenced by the nanotechnology nowadays, such as food, cosmetics, medicines, electronics, etc. For the manufacturers of the nanomaterials, the nanomaterials that they are producing are required to comply with some specific regulations, as you can see some examples in the slide. And in these regulations, it's stated the physicochemical characteristics of these nanomaterials for being permitted for the commercial use. To obtain these physicochemical characteristics, it is therefore necessary to develop validated and traceable measurement methods, as well as reference and quality control materials to, in the end, support the industry, reference and testing laboratories, and monitoring agencies as well. If we take a closer look at the definition of nanomaterial by the European Commission, and we can see that there are two main different measurements that we need to specify to determine what is a nanomaterial and what is not. One will be the particle number concentration, and the other one is the particle size distribution, that therefore should be always determined. But to obtain this type of information from an analytical perspective, there are some challenges that we need to face. And there are some points in which we can summarize these challenges, which normally are that these particles or nanomaterials are embedded in complex matrices, and there's a lack of validated methods for the extraction of these particles from these products. Also that these nanomaterials, mostly or part of the distribution is below 20 nanometers at the very lower end of the nanoscale, and for these sizes there are very few techniques available for the analysis of the particles. Also that we are facing a scenario that is far from being ideal and easy, in which we are facing some multimodal character and complex shapes of the particles in these products. And in the presentation today, we're going to focus from the two measurements that I mentioned before. We're going to focus on the particle number concentration. Single particle ICP-MS has emerged as an attractive technique for particle number concentration. I'm not going to go much into detail for the principles of the technique, but the main principle will be that we, under some specific conditions, we can measure signal intensities in time, and each signal intensity or event will correspond to a single particle. And by counting this number of events or pulses, we can relate that number to the particle number concentration that it's in our sample. But for that, we need to determine a specific parameter that is crucial in this case, and it's the transport efficiency. And for single particle ICP-MS, we can break down the methods within a single particle into different categories. The first one will be the methods with a reference material dependency, in which the signal is coming from a reference material. Or on the other hand, we have the reference material independent methods, which mostly are gravimetrical or microdroplet approaches. Within this second category for the independent reference material independent methods, we can find the dynamic mass flow, or DMF, which is the method that we developed within the NML a few years back. And the main principle for the DMF is that we are continuously monitoring two types of flows for the determination of the transport efficiency. The first one will be the mass flow of the sample that is reaching the plasma. And the second flow will be the sample uptake. And by relating these two different flows, we can determine the transport efficiency, and therefore we can calculate particle number concentration. The main advantages for this methodology is that since we are measuring flows, we can obtain direct traceability to the kilogram. It does not require the use of a reference material, because that can be applied specifically or directly to your sample. And the method can also be used for the characterization of the reference materials or quality control materials. So as we can see in this slide, the performance of the DMF has been checked against different types of nanomaterials, in which we can go from the simplest case that will be gold nanoparticles, spherical gold nanoparticles of two different sizes, 30 and 100. And from there, we move to far more complicated scenarios, such as titanium dioxide nanoparticles, in which they were no longer spherical but bipyramidal, and also organosilica bits of different sizes as well. And in the table, in the column in the middle, we can see them and the results obtained by the DMF that we were checking against an orthogonal technique, which in this case is the particle tracking analysis on the right-hand side. And we saw that for all the materials tested, the performance of the method was quite satisfactory. Also, the verification of the performance of the DMF was checked or verified through international comparison levels at the CCQM level, in which in this specific CCQM study, the sample of interest was the 30 nanometer gold nanomaterials, and as we can see on the graph, the results obtained by the DMF were completely in agreement with the consensus value for the CCQM study. And in parallel to these studies, this material, the 30 gold nanometer particles, was also used for the production and characterization of the quality control material that was named after LGCQC 5050. And we obtained an assessed value of particle number concentration with the DMF that was SIM traceable. On the right-hand side, we can see the certificate for this material. And the most important thing to state about this is that this was the first quality control nanomaterial in the world with a characterized value for particle number concentration. Apart from this validation through interlaboratory comparisons, the DMF methodology went also through a process of inclusion within the ISO documentation for the characterization of nano objects using single particle ICP-MS. And really recently, the method is also being accredited by the UCAS, in which the scope is specifically number-based concentration of metallic nanoparticles in suspension of equivalent spherical sizes ranging from 20 to 150 nanometers and concentration greater than 10 to the fourth particles per gram. So since the DMF methodology was included in this ISO documentation, and also there were an increasing number of laboratories that were incorporating the methodology, we decided to conduct a systematic study to test the operational boundaries of the method, and also to see its applicability to different instrumental setups, because in the original publication, it was stated for some specific conditions that we can see here in this slide on the right-hand side. And these conditions were the use of a Scott type spray chamber. The temperature of the spray chamber was controlled to 2 degrees to minimize the solvent vaporization, and the instrument was used in an equilibrium state. So considering these original conditions, there are some key considerations that we need to take into account, such as that was specifically for a specific hardware setup. Also, that we need to avoid the solvent vaporization, and that's why the temperature should be controlled. And also to assess that the solvent transport and the particle transport is the same for the determinations of number concentration. And to study these key considerations, we decided to use 2 different types of spray chambers to test the performance of the method with 2 different acquisition setups. On one hand, we have a Scott type spray chamber, and on the other hand, we have a cyclonic one. To test the temperature range, we went from the original conditions, which are 2 degrees, and we wanted to see the effect of the solvent vaporization to increase by increasing this temperature up to 15 degrees. And finally, for the flow rates, we studied a range in which normally most of the studies using single particle ICP-MS are using these conditions from 0.2 to 0.5 milliliters per minute. Then in this slide, we specify the experimental design, how it was for this expansion of the boundaries, in which on one hand, we have one instrumental setup, which is the Agilent 8900 triple quad, with the Scott type spray chamber and using dwell times in the range of the microseconds. And on the other hand, we have ICP-MS from TOFWork, in which the spray chamber is a cyclonic one that is also used in the thermo ICAP. And the dwell times in this case are in the milliseconds. And then we compare the performance of these 2 different instrumental setups for same flow rate conditions and acquisition times. And the sample that was decided for these studies was 60 nanometer gold nanoparticles in citrate. And to check the performance of the DMF, we compared the results that we obtained against a specific number concentration value from an intercomparison interlab study at a CCQM level. So we are presenting all the results in terms of recovery against this concentration value. So first, we want to show the results for the acquisition setups with the original temperature conditions. And as we can see in the table, the performance of the DMF was suitable for both instrumental setups with good recoveries in both cases. Then moving to the study of the temperature range with the ILN 8900 with a Scott type spray chamber. We see there is a trend for the, as we increase the temperature of the spray chamber, then the recoveries are dropping. Considering in the graph at the bottom of the slide with the CCQM value in red and with the dashed lines as the uncertainties with a coverage factor of 1, we can determine that the results obtained from 2 degrees up to 6 degrees were still within the uncertainty, so it is still suitable for the accurate number concentration determination with the DMF. That's what we saw with the Agilent 8900, but when we used the software instrumentation with a cyclonic spray chamber, the results were a bit different, in which what we can see is a plateau that was increased from 2 degrees up to 8 degrees in this case, in which we were still obtaining a suitable number concentration determination by the DMF. And regarding the uptake flow rate range for the Agilent 8900 with the Scott type spray chamber is that, of course, we can see that the transport efficiency varies with the uptake flow, but in all the cases and in all the ranges studied, we were still obtaining an accurate number concentration determination. And similar results were observed for the software instrumentation using a cyclonic spray chamber. So to finish the presentation, I would like to highlight again that the NML developed an SI traceable approach for nanomaterials number-based quantifications with single particle ICP-MS, and the performance of this methodology, the DMF, was demonstrated through interlab comparisons at the CCQM level. The methodology was standardized under ISO documentation, and also it's been accredited really recently. Testing the operational boundaries of the method, what we saw is that the DMF is compatible with different instrumental setups. Also, that is compatible with temperatures of the spray chamber ranging from 2 to 6 degrees. And also that is compatible with sample uptakes flowing, ranging, from 0.2 to 0.5 milliliters per minute. And the last point, but I would say it's the most important one, is this. Under these optimal conditions, the DMF method could be invaluable because of the characterization of for the characterization of reference materials for number concentration. And this type of information is really important because these materials are desperately needed to support the industry, the public sector, and also analytical testing laboratories. So finally, I would like to say thanks to all the people involved in this story about the DMF, which involve people from the NML at different levels, such as the reference materials team, the statistics team, and of course the inorganic analysis team. So thank you so much for your attention.
Thank you so much, David, for giving us some insights into the DMF, into the method. And we are happy to take maybe only one question, please, by raising the hand or in the chat. Is no one? Thank you, Hakan, for answering in detail the question of Moses. And if nobody has a question for David, maybe I will try my luck again, a short one and with a short answer. The method is standardized, it's relatively new. I don't know it in detail, but what about this threshold, or is there a threshold for this recovery rate? Is this also part of the standard? how to find this threshold. Acceptable recovery rate and not acceptable.
So in this case, we were checking against the values from number concentration recoveries against this consensus value for this material at a CCQM level, and we were considering that if it's within the uncertainties, considering a cover factor of 1 because it's statistically a restrictive case, then the performance of the DMF is still accurate for number concentration.
Okay, this was the other column what you have checked. So you check it by R. Okay.
Mm-hmm.
Good. Thank you. And Dorota, you agree? We continue then with thank you so much once again to David. We see us again in the panelist round. And we are happy to have Vikram and the first slide. Welcome, Vikram, in the round. We have introduced you at the beginning of the meeting, and we're happy to have you with the talk about accurate size measurement of 2 new particulate materials from JRC. Please.
Well, now the microphone on. I hope you can also hear me. And first of all, before I start, I would like to thank both you, Dan, and Dorota for organizing this webinar, and also to provide me with the floor to give let's say an update or to present a very specific reference material project that was finalized last year. I don't know if you see my slides.
We see your slides, but not the presentation mode. If we can activate it, is perfect.
Let's now it should work.
Perfect.
Hopefully. Yes. Okay,
Excellent.
Great. Thank you. So yes, thanks a lot again. And yeah, during the next 20 minutes, I would like to present a project, a reference material project, or actually 2 projects, which resulted in 2 materials, 2 new certified reference materials labeled as ERM FD104 and ERM FD105. And I will explain you exactly what these 2 codes mean later on. And of course, this work was not only done by me, but by a whole team of colleagues. And this work was done at the European Commission Joint Research Center, where I work already for 20 years. And since a few years, I'm there also the quality manager. And I know that Håkan has been talking already about reference materials, certified reference materials, the difference. But before I go into these 2 new materials that we developed last year, I need to bring you a little bit, or I need to give you a little bit of background information. And it was also actually mentioned by David. He mentioned about the regulatory frameworks, in particular some pieces of legislation in the EU that contain provisions for nanomaterials. And of course, these provisions have been put in place to protect health and environment for potential risks. And David also referred to the European Commission definition. It's a recommendation. But here you will see that I'm referring to an older definition. And for history, I need to do this because the very first definition that was put in place by the European Commission was a definition from 2011. For the first time providing a regulatory definition for the term nanomaterials, because as you know, we have different pieces of legislation. They contain nanomaterial provisions, but of course it's very important to have a common understanding of what a nanomaterial is. And this very first definition was mentioning, or was explaining a nanomaterial as a material containing particles in an unbound state, or as an aggregate or agglomerate, and where for 50% or more of the particles in the number size distribution, 1 or more external dimensions is in the range of 1 to 100 nanometers. And you will say, this is very much the same as the definition that was mentioned by David, and I will come back to that. But there are some important differences. But of course, to implement this definition and to also help the implementation of the sectoral legislation that contains these nanomaterial provisions, such as the directive on cosmetics or novel foods or in vitro diagnostic devices, for example, we need to have, on the one hand, validated methods, and on the other hand, we also need certified reference materials. And again, Håkan mentioned this already in his talk, that it's very important to have good methods, because without good methods, it's impossible to make good reference materials, and the other way around. So it's always this chicken and egg issue. So to help the implementation of these definitions, of the definition and the legislation, we developed reference materials, and we started with the very first reference material for nanomaterial reference material, basically already more than 15 years ago. I would say it was around 2010. So more than 2010, I think we started to develop the first materials, and these very first materials were basically silica materials, suspensions, having basically near spherical shapes, and they were suspended in an aqueous suspension. They were either monomodal or bimodal, and they were certified for different equivalent spherical diameters or measurements. And we used different methods to characterize the reference materials, such as dynamic light scattering, centrifugal liquid sedimentation, small angle X-ray scattering, particle tracking analysis, and both scanning and transmission electron microscopy. And these materials, these reference materials, these suspensions, they are mainly used for quality control purposes, but also for method validation, and in some cases even they can be used for calibration of the methods. Now, most of you, I mean, you know this, but I would like to remind you again about it. The fact that we use different methods to characterize the reference materials, the nanoparticles, is because these particles do not have a very spherical shape. They have a near spherical shape, but they are not perfectly spheres. And because of that, different methods basically measure the same particle, but they can give some different results, as can be seen on this graph here. Results, for example, obtained by dynamic light scattering for the same particle would result in 89.5 nanometers. But for example, with particle tracking analysis, you could have results ranging from 82 nanometers to 87 nanometers. Or when you would measure the same particle with atomic force microscopy, you would measure 80 nanometers. So there are some differences, and these differences can be explained because, again, these particles do not have a perfectly spherical shape, and that means that they have many different external dimensions. And on the other hand, the methods are relying on different physical measurement principles. And for that reason, we are certifying different sizes. And what I also would like to mention here is that the production of nanoparticle reference materials, we had to go from let's say a simple approach, focusing on monomodal silica particles, to more complicated materials. For example, in the next materials that we produced were not monomodal anymore, but bimodal. So for example, here this ERM FD102, where we had a mixture of 20 and 80 nanometer particles. Or at the next stage, we moved away from near spherical shapes, but we went to nanorods, such as this example here, titanium dioxide nanorods. So the production of reference materials is often following what we call an iterative process. So we have to start with something simple, and gradually we make something more challenging, because the particles, the industrially relevant particles that we have to analyze, are often not perfectly spherical. They do not have a spherical shape, but they can have very irregular shapes. And this is also why it takes so much time to make reference materials, because we have to go from a simple model reference material to something that is closely matching industrially relevant particles. Now, we have been from 2010 till 2017, we have been focusing primarily on I would call them more easy materials. But as you know, many industrial nanomaterials are not suspensions, but they are powders. And to support the measurement field with methods and reference materials for powders. There was the nano-defined project. It was EU funded. It ran from 2013 to 2017. And in that project, the consortium partners, they have been developing very specific methods to measure these particles and also validating the methods. And they had, the main purpose was basically to help the implementation of the nanomaterial definition, the old definition, the definition from 2011. But in 2022, we had a new definition because the old definition contained some, let's say, ambiguous terms. And one of these ambiguous terms was basically, it was referring to agglomerates and aggregates, but it was not clear from that definition what to do with agglomerates and aggregates, how to measure them. Did we have to measure the agglomerates and the aggregates as one single particle, or did we have to look inside the particles? And this was changed in the 2022 definition, which was referred by David. And then a very important new term that has been introduced in that definition is the term constituent particles. And this means basically that for the measurement of nanomaterials according to this new definition, you have to look at the constituent particles, or sometimes also referred to the primary particles within agglomerates and aggregates. And in having that in mind, we developed two new certified reference materials, this ERM FD104 and ERM FD105, which has been characterized for the constituent particles. And here on this slide, you see two representative electron microscope micrographs. On the one hand, FD104, which is an alumina-coated titanium dioxide. You can see it has an irregular agglomerated, irregular shape, and the material is highly agglomerated. And according to the definition, this material is not nano, but it has a very small fraction of particles with a nano, in the nanoscale. On the other hand, you have the FD105 material. It's not titanium dioxide, but it's a barium sulfate material. And you can see that it is much more aggregated. So it has also irregular particle shapes. And here this material is a nanomaterial. So most of the particles have a size below 100 nanometer. And these were the two materials that we have developed. And for the measurements of these particles, we looked at very specific measurements for electron microscopy, because basically electron microscopy is one of the few methods available that can really measure the constituent particles inside agglomerates and aggregates. And the measurements that we have been looking at were basically the Ferri diameters, both the Fmax and the Fmin. We have also been looking at the maximum inscribed circular diameter and the equivalent circular diameter. And then we have been looking at the particle size characteristics, such as the mode, the median, and very different percentiles, such as the D5, D10, 25, 75, 90, and 95. Now, when we do a characterization of a reference material, we involve different laboratories, and depending on the material, we ask them to basically follow a very specific protocol or to follow their own method of choice. Now, in this case, we want, as also explained by Håkan, the measurement uncertainty of the certified values is important. They should not be too high, and we decided that we should not give a full, let's say, flexibility to the laboratories, and but to provide some, let's say, common parts of the measurement protocol. And we have provided some basics to the laboratories. So let's put them first. First aspect was basically we told them how to prepare a sample, meaning that they had to transfer a certain quantity of the powder into a specific liquid, a suspending medium. They had to apply some sonication and then to transfer a portion of the suspension onto a grid or a stub, and then to apply electron microscopy, scanning all transmission electron microscopy, and to measure at least 1,000 particles per grid. We used the electron microscopy results for both homogeneity and stability testing. I will go very quickly over this slide, just to indicate basically that here we measured even more particles per specimen, so 5,000 instead of 1,000, just to make sure that the measurement uncertainties were as small as possible. We looked at different storage intervals, so up from 0 to 4 weeks of storage at different temperatures, and we measured 2 units per time point. And on the right-hand side, you can see some uncertainties. So basically, the uncertainty for homogeneity varied between 1.5 and 2%. So depending on the material and depending on the measurand. And for the stability, you can see that the uncertainty ranged from 0.4 to about 0.6, 0.8%. So very small. Then again, going to the characterization, we used the electron microscopy methods, scanning and transmission electron microscopy, and the characterization was done by a network of competent and preliminary qualified laboratories that basically adhered to the principles of ISO 17025 standard. And just to give you an idea, we invited about 14 expert laboratories to participate in the study. But in the end, only 4 laboratories were able to do so, because these were the only ones who had basically the measurement of powders in their scope. So many laboratories need to measure nowadays powder nanomaterials, but from expert laboratories, we were only able to find few laboratories who were able and willing to measure the materials. So also highlighting the complexity and the many challenges that are related to measuring nanoparticles when they are in a powder form. Again, we provided the laboratories that participated in the characterization study with the measurement protocol that we developed. And along with that measurement protocol, we also provided some quality control samples, which was a former colloidal silica certified reference material. And we used that material as a kind of control to validate the results on the candidate reference materials. So when we look at the data sets of the candidate reference materials, we first look at the results of the quality control sample. And if these results are fine, then we also look at the results of the candidate reference materials. But if the laboratory would have issues to measure the quality control sample correctly, that could be a reason for us to eliminate the data set on the candidate reference material. So the laboratories had to measure 1,000 constituent particles. Here, I can mention that for some laboratories that went quite straightforward, because they could analyze the particles in a semi or in a fully automated manner. But there were also laboratories who had to do the counting manually, and well, measuring 1,000 constituent particles per grid or per stop, that's quite time consuming. So we also saw some differences there. Again, the labs used the pre-developed protocols, but basically for the actual preparation of the grids and the stops, we gave some flexibility to the laboratories to use their in-house methods. We had a lot of, because as I mentioned earlier, we asked the laboratories to look at very different measurements: maximum Ferrier diameter, minimum Ferrier diameter, equivalent circular diameter, to look at the particle size distribution and at the mean model diameters plus some percentiles. So we had a lot of data sets. Here I only give a few results, but basically all the results are very similar in that respect. For example, here you see the results for ERM FD104, the titanium dioxide, and both the median and the model value of the minimum Ferrier diameter. And you see that the results are overlapping the certified range. But you can see some differences in measurement uncertainty. So in the error bars, for some data sets, we have smaller uncertainties. For other data sets, we have some larger uncertainties. And this is linked to basically the reproducibility of the method that was employed by the laboratories. The same here. This is for ERM FD105, the barium sulfate reference material. Same observation. Most of the results agreed well with, but for some laboratories we see small uncertainties. For other laboratories or data sets, we see quite large uncertainties. And then on the certificates, we present the results like this. So it's we have the results for the different measurements. So it's quite a number. And the results indicated in blue are also shown basically in the graph, in the cumulative distribution, both for FD104 and here for ERM FD105. In conclusion, we'll put them all. So ERM FD104 and ERM FD105 are the world's first powder certified reference materials, certified for different characteristic values of number-based size distributions based on constituent particles. So again, we are looking here at the individual primary particles measured within agglomerates and aggregates. These materials are industry relevant. They are commonly used in industry, and their main purpose is basically the verification and the validation of electron microscopy methods. And they're mainly intended to help the implementation of the European Commission nanomaterial definition, the new definition from 2022, and related legislation. And by that, I would like to thank you. And it's not mentioned here, but in particular, I would like to thank all the laboratories and experts that have been contributing to the development of these two materials, because without the networks we have, it's impossible to make such complicated materials and to characterize such materials. Thank you again.
Thank you very much, Vikram. I like also the order of the talks in this webinar. We see now, we notice that we are increasing the degree of complexity of what we analyze here and the associated problems, but it is possible if you have the right expertise. And how important is maybe only one comment. You can formulate one question, please, in the chat or by raising the hand. How important is to have well-prepared protocols? I was also part of this study, and the better these protocols are prepared, the more you invest in the measurement protocols, the more you spare in the time, in the efficiency, and in the accuracy of the final results. Okay, only good words, but still no question, maybe direct question, because the study was so good for both materials. Then I propose, looking also at the time, in the light of the time, to go further. Let's thank again to Vikram. Thank you very much. And going to Andreas Thünemann with a talk on development of nanoplastics in my own institute. Please, Andreas.
Okay, I share the slides. Can you see it?
It's coming. I still see something white, a white background, but not more. The same for the now we have the first slide, and if
Okay.
you activate the presentation mode, we are done.
Can you see it?
Perfect. Please. Yeah.
Okay. Yeah. Then I will hurry up. So I will report on the development of nanoplastics reference materials at BAM. BAM produces already microplastic particles, and 4 reference materials are in the BAM webshop, and we hope that next year we have also some nanoplastics reference materials. So first I will introduce some things I think are important in this direction, and today I will discuss only aqueous dispersions of nanoplastics. Yeah, so we always have the particles in water. The first is nanopolypropylene, then I go to nanopolyethylene, nanopolyethylene terephthalate, then some on polylactic acid, labeled and non-labeled, and some summary what we are doing at the moment in our research. So at the moment, the global emission of plastic waste is about 52 metric tons per year. That means that about 25% of all produced plastics is not collected in any way. This is so much that it is not wondering that all over the world you can find plastic particles. So just a reminder, macroplastics means particles of larger than 5 millimeters. Microplastic is particles between 1 micrometer and 5 millimeter, and nanoplastics is all particles below 1 micrometers. So this is a little bit different to the definitions of nanoparticles, which means particles with 1 dimension less than 100 nanometers, not to be confused. So the worldwide plastic pollution, you can see here the total emissions, and you can see that in North America and in Europe, the total amount of waste not collected properly is much less than, let's say, the highest values in India. So there are regions in the world where there is no collection of the waste at all. So macroplastic goes to microplastics. The amount of microplastics in the world is already relatively well known, but no one knows how much and how well distributed nanoplastics is at the moment. This was the beginning of PhD thesis in my group. The idea from people working in toxicology, they wanted to have the plastic particles without any stabilizers. Yeah. So normally, if you have particles in waters, you need stabilizers like surfactants. We developed a method which is very easy, and this works for polypropylene, polyethylene, and polyethylene terephthalate. We start with a few grams of the polymers. Then we grind them in acetone at low temperature, typically minus 20 degrees Celsius. Then we filtered it, added water, and then removed the acetone and filtered it again. And then you have nanoplastics in water, and these surfaces are not spherical. So all the particles, as you can see here in the SEM picture from Dan's group, means that the surfaces of these particles is very rough. And we believe that this is relatively close to what we found in the environment. The disadvantage is that the concentration of the particles is very low. So for example, here you see polyethylene and polypropylene. You see this is slightly turbid, so particles are in there. The setup potential is low. In the case of polypropylene, this is about minus 30, and for polyethylene, it is less than minus 40 millivolts. And this explains why these particles, meanwhile, are stable in solution for 3 years. So after some storage time, you see some white on the top of the suspension, but after vortexing for 30 seconds, the solutions are homogeneous again. The diameter of the particles does not depend much on the type of polymer in this case. So for polypropylene, it's a little bit different to polyethylene, something around 146, 126 nanometers. And the polymer concentration is in the range of typically 20 to 40 micrograms per milliliters. So this is relatively low. I said the particles are stable for long terms in this aqueous solution. So I want to mention that before filling the particles, in the vials, we heated the particles up to 80 degrees C for 3 hours, just to make sure that not much microorganisms are still in the bottles. Because we have only water and polymers, and that means, there may be some microorganisms grow in these vials. So the theta potential as a function of the pH decreases obviously when we add acid, and then it becomes unstable. So these curves are very similar for the polypropylene and polyethylene, and also for polyethylene terephthalate. One of the reviewers asked us what happens if you use different molecular mass. We use this molecular mass of relative low weight of 10,000 grams per mole, but also 150,000 grams per mole. And we see that there is no difference significant in the particle sizes and theta potential. And we see also that the molecular mass did not degrade due to the preparation procedure. But if you add salt, as from colloidal stability, you expect that at high salt concentration, at 0.9 grams per liter, it aggregates relatively fast. Within an hour, you have about 50% aggregates. And if you have a little bit lower salt of 0.09 grams per liter, then the aggregation becomes a little bit more complicated. But when you use it in cell culture experiments, then you have to be aware that your particles start to aggregate if you use it in your cell toxicology experiments. The next step was that we want to have labeled polymers, and we started to produce gold clusters. It took us some time to find out the right method. So these gold clusters have a diameter of about nanometers, and the production was published, and we were able to incorporate these gold particles into polylactic acid nanoparticles. These polylactic acid nanoparticles were not produced mechanically. They were produced by the so-called nanoprecipitation methods, which allows us to include the gold clusters in the polylactic acid particles. You see this here, nanopolylactic acid without, with 0.8 weight percent gold and 5% gold in the particles. So size exclusion chromatography proves that the gold particles are really in the incorporated in the nanoplastics particles, and this was supported also by the UV spectroscopy. Very recently we worked together with an initiative in Halle, and the initiative will care about nanoplastics released from medical devices. And preliminary investigations were done on PET and also a new polymer, which is polyethylene furanoate, which is biodegradable and can be made from natural sources. So PEF can replace PET in the future. We used our dispersion methods that works also very nice for the PEF. You see this in the bottles NP1 and NP2. Then we use confined impinged jet. This is also a method which produces spherical particles, but you use hexafluoroisopropanol during the synthesis, but the particle preparation goes quite well. And then we use a precipitation method in DMSO, but in this case with the help of a stabilizer pluronic, which allows us also to incorporate fluorescence dye, which is well known in cell culture experiments. So PEF and PET are available labeled with these Alexa dyes, and we just published a first publication where we see this labeled nanoparticles in cell culture experiments. So here you have an overview on the PEF and PET particles. You see that the high setup potentials on the right side are always present if we use some mechanical precipitation methods. The disadvantage, as you see, is that the concentration is very low. If we use this nanoprecipitation method, the concentration is a factor of 1,000 larger. But with the disadvantage that you have to accept stabilizer. Here in this case, we use pluronic F127, which is a very biocompatible stabilizer and which is also FDA approved for medical applications. Here you see an overview on these different particles. All the particles size distributions are monomodal. Some of them are already very narrow, but all are monomodal. And as I said, if nanoprecipitation was used, then the particles are close to spherical, and if mechanical degradation is used, the particles, surfaces are very rough. We published also a first study on the interference of the particles with, in this case, lactoglobulin. So in the first row, you see how the lactoglobulin adsorbs two particles. On the left-hand side, it's the silica particles. We have very high affinity of the protein. With the polylactic acid particles, there's a high affinity, and the polyethylene terephthalate particles more or less reject the adsorption of lactoglobulin particles. Then we looked at the protein folding, and you see on the surfaces of the silica particles, there's a strong unfolding of the particles, and this seems to produce a low cell viability. The polylactic acid particles, the refolding of the lactoglobulin is low, and there's only minor effects. And the protein on the polyethylene terephthalate particles, we see minor changes in the structure of the protein and no cytotoxic effects. So that means depending on the particles, the possible toxic effects are very much different. And at the moment, we submitted a paper where we use the same method to investigate how enzymes change their activity when they interact with nanoplastics. Yeah, I come to a summary. So nanoplastics, I think, is a key for future risk assessment of these particles. Reference materials may help to quantify the amount of nanoplastics in various environments. On the way is nanopolypropylene. This publication is available for 2 years, and many groups in the world use the method meanwhile to produce their own reference. And nanopolyethylene is available, nano-PET is available, and also nano-lactic acid, labeled or unlabeled with gold. Yeah, the work was done by Tina Rübach, Maximilian Ewitsch. They did a lot of synthesis. So each synthesis was reproduced at least 60 times. So from 60 repetitions, you can say that about 57 repetitions are quite reproducible. Petra Fengler did the light scattering experiments. Kerstin Rademann tried to investigate the particles with small angle X-ray scattering. Andreas Taubert helped in the ionic liquid synthesis of the gold clusters. And Jana Hildebrand performed her PhD thesis on nanoplastics. And thank you very much for your attention.
Thank you very much, Andreas. And I'm also looking at Dorota, and the hand is not raised. So for staying in time and being relatively well again together in the program. Do we have one question for Andreas? Is the last talk? We have seen the developments at BAM with a set with several materials, nanoplastic materials. And I'm looking into the chat and also no question. But it doesn't mean that you will not come to some questions and interaction. With this, Dorota, we proceed then to the second or to the last part of this last quarter of this webinar, where we will have a little bit more interaction between the participants and the panelists. And Dorota, you take it over with Guillermo, and let's see how good this works now.
Okay, thank you, Dan. Let's move on to the interactive session that will use Slido. So my colleague Guillermo will now activate the Slido component. So you should be able to see the questions in the chat very shortly. I would also ask Guillermo to share his screen, where you will be able to see the results coming in real time. The first question that we'll have for you, it's a question that it's a multiple choice. So please select all answers that apply to you. It's about the parameters of the nanomaterials that you require for your application and which parameters you need reliably characterized. So if you see in the chat, the first questions just appeared, so please start voting. And Guillermo, please, could you share your screen so we can see answers coming in real time? And while we are waiting for all the attendees to hopefully wake up in the excitement and give us your answers, we can also start discussion sessions with our speakers, with the panelists. And the first question, since I'm talking, maybe Dan, I can ask, and then you can ask yours. So I've got a question which I would like to ask Hakan. So you have talked in your presentation earlier a lot about the definitions, but I would like to ask once more for you to explain to all the attendees and to all of us, what's the difference in a simple terms between a reference material and this highest order certified reference material?
Yeah, a certified reference material is a reference material, but all reference materials are not certified. That is to say that all reference materials have to be sufficiently homogeneous and stable for their intended use in a measurement process. But the certified reference materials they are sufficiently homogeneous and stable, but they also have a certified parameter which is traceable to a common point of reference, and an expression of the measurement uncertainty that is associated with that certified value. So indeed, in terms of hierarchical metrological order, a certified reference material is on top, but from the point of view of a definition, the reference material is on top. So that's why certified reference materials are good for dispute resolutions in court cases and so on. So it's just enough. I think I stop there. Yeah.
Fantastic. Thank you for explaining once more what the difference is. I hope everybody understands. Dan, shall we continue with the questions about the CRM and RM?
We continue with the questions, fine. But shall we comment maybe? Yeah, we have 24 answers now. How do we proceed now with the poll, with the active?
So I think we can wait a little bit more for other attendees to answer and move on to question 2 to the panelists. So please, if you have troubles answering, you can also go to the Slido by scanning this QR code and using your phone if that's easier.
Okay, because we see here 25 answers from 51 participants, so please, it's still potential. Okay, then we continue with the next question. And I don't know, Vikram, if you are no more with us. You are. I see you without picture, but let's ask. I emit the question and let's see who can answer. Why at all do we need a certified reference materials? We have seen this famous term traceability. Can we put together this answer? Why do we need reference materials and namely being certified? Wants to answer is one of the most easiest, or in fact in each talk highlighted, but maybe we can put it as a conclusion together.
Perhaps we can ask David to answer, because we saw a lot about the methods and applications. So why do you need certified reference materials?
Yeah, I can take this one if you don't mind. So it's all about the traceability in the end, that it was mentioned also during the first talks, and Hakam, a very illustrative talk about the traceability as well. So it is really important because then from a metrological perspective, you are obtaining some reliable values. And this is really important because it was also mentioned during the talks that it is really important at different levels. One would be for the development of new methodologies that can be applied for the characterization of nanomaterials, but also it's a way to validate methods that are already developed. We're also gaining a lot of comparability as well. And this type of information can also be used at different levels, such as industry in general, but also for monitoring or regulatory agencies for trying to achieve this regulatory compliance. Right.
Okay, thank you so much. I think you have put together all the most important elements as part of this answer, with, on the first place, having this famous traceability. I'm also seeing that the number of participants is decreasing, but the number of answers is increasing. The ratio is much better, and we have some clear winners. Dorota, you have the word. How do we proceed? Shall we stop maybe and come to the next poll question?
I think so. Maybe we can just summarize what we've seen, because we already have clear winners here. So most of the attendees have answered their particle size and particle number concentration are the key measurements, which is great because we've got certified reference materials for the particle size, whilst for the particle number concentration, we've got a quality control material with SI traceable characterization value. And I know that my colleagues from the reference material team have got plans to release also a certified reference material in the near future characterized for this parameter. Other measurements are important as well, but there is still, I think, work to be done, especially for refractive index or particle density. So with that, I will ask my colleague Guillermo to close this poll and open the second poll, which maybe is even more exciting. The second poll question that we have is an open question where you can type in your answer, and the answers will appear on the screen as kind of a heat map. Or a cloud. So we will see in a minute in the chat this second question activated, and you can start voting now. So while we're waiting for the attendees and participants to give their answers, we can continue with our questions to the panelists. And if attendees have got some more questions that they would now like to ask, please also type them in the chat. So I have a question while we're waiting for some questions from attendees and waiting for the answers to the poll. I have a question to Andreas. Digitalization and automation are a very hot topic these days. So my question to you would be, to what extent the automation can support certification of or characterization process in reference material development?
Do you mean me?
Yes, please. Question to you, Andreas. Sorry. Yes.
I think at the moment, automation is not the bottleneck of production of reference materials. Yeah. So automation is then good when you want to produce day and day. So, but if you produce 1,000 vials, for example, yeah, then you can do this also by hand. This is I believe the certification process is more or less the bottleneck. Or to get the right candidate materials, yeah.
Okay, that's a very interesting answer. So maybe I would have then a follow-up question to you. So what do you think is the key barrier and technical limitation in reference material production, and what's the typical size of the batch that you would be preparing?
Yeah, typically 1,000 or 5,000. And this is work in the lab for, let's say, 3 weeks, yeah. And it becomes faster if you have an automatic process, but only if you want to produce very similar things again and again. If you want to have a completely different reference material, you start to do the automation from scratch, typically.
Okay.
This is my opinion. Maybe I'm wrong, but this is what I see. If you need, say, 1 million batches, it's completely different. Yeah. Digitalization is a different story. That helps quite much. Yeah, to make the data have to make fair. Yeah, and then digitalization helps much. Not to have all these Excel sheets where you have to look at every, or if you change something, yeah, then the automatic process of the data treatment. This is very helpful.
I understand, and thank you for this answer and explaining the difference between automation in reference material production and digitalization in terms of the data treatment itself.
For the second, the digitalization, we at BAM at the moment, we have the data store, yeah, and we try to fill all our data in this data store so that you can read and find this quite better as in the moment.
Yes, that's clear. Fantastic. So thank you for explaining us the difference and how that works in the context of reference material. Dan, do you have a follow-up question maybe, or also if other speakers would like to comment on that topic, please, as well?
We are well prepared, and I have a follow-up question. And I am impressed by probably by the diversity of answers to the question regarding limitations and having maybe some winners, but we'll come back. Yeah, 29 answers from 47. So let's take the next question, as long as you are introducing still your answers. A question to Hakan, please. We come back to you. What about development of reference materials or certified reference materials being characterized for only one parameter, which is the classical, let's say, way, or how big is the effort, and if it is worthy at all to develop one reference material for several parameters? How successful is this approach?
Yeah, this is an interesting question because that's almost philosophical. We know, for example, that NIST tend to certify a lot of parameters in their materials. And we, as a contrast, have perhaps traditionally have had less parameters certified in our materials. It could be for the simple reasons that they have had access. More trouble to access and process reference materials in-house in their facilities. So they have certified more parameters in the materials that they have had available at the time of certification. For every parameter, there needs to be dedicated studies. That adds to the complexity. It delays also the process of certifying. So if you want to get a certified reference material out faster, you need to have fewer parameters certified in the materials. On the other hand, others are more let's say family, I mean, LCMS, you can have hundreds of compounds in one run. So it just depends. Access to good calibrants and good studies, you can certify more parameters at the time. But I mean, so it's a little bit the balance. How fast do you want to release it? What you said from the beginning surprised me a little bit, because we are traditionally not just aiming to certify one parameter in the material. So a study can be set up around a handful of parameters in one material. That's what we normally try to strive for, at least at the JRC.
Okay, thank you, Hakan. Okay, and the basic approach is to certify as much as possible and reliable, and not only one, and to put the maximum effort in all.
I would like to add one thing from before. The certified reference materials is a trueness check. Not only about traceability, the trueness check is very important, because you can have a reference material, a non-certified one, that is very useful for purpose of a control chart, for example, but there could be a bias in there to the actual true value. The certified value should reflect the true value within a 95% confidence interval normally, given the coverage factor of the uncertainty that is associated with it. So indeed, the trueness check is a super important aspect of the use of a certified reference material.
Thank you, Hakan. Also important from the other experiences of this bias or the trueness is and the most critical part. Or in most cases, the analysts are struggling with this component of the accuracy. Okay. We have 31 answers, and the number is stable meanwhile, and the variety is large. Now, how do we comment to interpret this?
The variety is large, but I think some answers have been given multiple times. We see them in the bigger font, and I see two right in the center, traceability and also matrix effects. And this is exactly what we've heard from our speakers today. Hakan talked about the matrix effect. We heard traceability a lot from all our speakers. So I think this is in line to what we have learned today. These are the limitations indeed, and very important points. So with that, I think we can close this poll and open the final poll. Guillermo, please, if you could activate the final poll. Final poll is about materials that the project ConcenSus is planning to develop, and we would like to know which ones. You can select 3 from that list would be of interest to you. So this is your chance to give us a little bit direction, and maybe also to the reference materials producers that are here with us today, to see what the community would really like to have, what's the next material that's of importance to them. I can see a hand up from Andreas. Andreas, please go ahead.
I have a question. If liposomes loaded with cisplatin, so cisplatin is a drug against cancer, then many laboratories are not allowed to work with it. Is this true? As far as I know, we are not allowed to deal with cancer drugs in our chemical lab.
So a lot of chemical labs are allowed to work with these chemicals, like with any other chemicals. So I suppose it's depending on the type of laboratories that would require this material. But we have it included in the project, and all the participants of the project can measure it within their lab. And this material can be made available as a representative test material to the wider community. But it's interesting to know what the community would require. Talking about representative test materials, research grade materials, is that something that our speakers would think that can be promoted since the development of certified reference material is such a difficult and long process? Is that something useful to the community, and would you support adopting such materials like the research grade materials and representative test materials. And maybe I would direct this question to Hakan, please.
Yeah, the short answer is absolutely yes. I mean, this is missing. There is no. There are islands. There are certain the research grade test materials. They are available from NIST. Indeed, there are such things, but it's not a consolidated approach. It would need that reporting database for it to be useful both for the users and the reference material producers. And we are looking into this in the JRC. So we have also spoken last year a bit with colleagues from BAM when we met in Canada. I think it's definitely a need for this. But let's see how far we can get with putting a concept together and find people who are willing to contribute. We also spoke a little bit about what would be the incentive for laboratories to report into such a database and so on. There are because otherwise it's of limited use both for other laboratories and for the reference material producers. There are a lot of aspects to solve or discuss before you launch such a program. But I definitely think it's needed, and it's basically missing today from, let's say, more systematic point of view.
Thank you. I could not agree more with this. I think the number of answers in the poll have stabilized, but we can perhaps leave it open while we ask one final question in the panel discussion session. Dan, please, could you go ahead with the final question?
You want to have the number 30. Okay, it is there. Yeah, somebody has put the 13th vote. Yeah, let's take another question, and the last one. Maybe to Andreas, from BAM to BAM. What are the requirements in terms of homogeneity and stability evaluation in the characterization assessment value of reference materials and certified reference materials? So this was so in the stability and homogeneity, what is what are the requirements for stability and homogeneity? Sometimes it's very critical. We have seen particularly for organic materials.
So for dispersions, homogeneity is not a problem, but stability is typically, And you can consider this as a product like milk, so you can store this for some time. Homogeneity is not a problem, but stability is always.
But stability, how? Because there are many examples, and the more complex are the sample and more organic, the more unstable. It's probably a general issue. Which approaches would we have, or it is possible, thinking at the previous question, research degree materials, to develop samples materials with a very short lifetime, for example, would be one approach. Or giving a curve, predefined curve of this stability.
Yeah, or we have to come to on demand. But this will make completely different procedures, and certifications. Typically, you expect a lifetime of at least 3 years, So you can produce much more type of materials if you just produce them when the customer asks for it, produce it and submit it,
Okay, but this would be a high requirement, or for the producers. I can imagine, I don't know how easy it is to do this. It's good for the clients, for the customers, but challenging for us, question mark?
Yeah, it is challenging, but this opens a complete new fields of reference materials,
Okay, then you see
for
that
example, your liposomes here, yeah. So
yeah.
liposomes, many type of liposomes that are not stable for a long time. Or you have at least store them at minus 80 degrees C under defined conditions, yeah. But typically production of liposomes with a stability of, let's say, 4 weeks is not a problem, but to guarantee the stability of liposomes for 3 or 5 years, when you include the reference production, yeah, then typically from production to end of lifetime, you need guaranteed stability of 5 years, which is for something like liposomes hardly possible.
Okay, but you mean this production maybe and closing with this being the last comment, coming to this production on demand. Customer wants some liposomes from BAM or LGC, and we are in the situation to produce this on demand, but being available or being stable only for 4 weeks. This would mean
typically, or let's say 3 months, something
or 3 months for a short time.
Yeah.
But this means we are the institutes, certifying institutes should be continuously ready to produce such materials. So is this availability every time? Scares me a little bit.
Yeah, and if you then have an automatic production and robots, then it's easy. So if the robot protocol is ready, then you type in what you need and the robot takes it. And the next morning, the samples are ready and filled. And then, then it really makes sense to have it with robots and automatization. Yeah.
Okay, I think it's a very good final statement, an optimistic one coming from you, Andreas, and combining different elements and thinking or having an outlook. Yeah, how in which direction we could evolve with the reference materials. And with this, Dorota. The number is stable here, 30.
Yes, I think we can close the poll. So interestingly, liposomes are not the top of the list. I think the polypropylene, PET plastics, nanoplastics, silver, nanoparticles that are already possible to, I think, be produced as reference materials or representative test materials come in first place. So liposomes will come maybe later. They are needed, but it's not easy to produce them because of the stability issues Andreas mentioned. So let's see what the future of the reference material production will be. It could be that what we have just discussed. It's a vision. I think with that we can close the poll. Thank you, Guillermo. So if you could stop sharing your screen, maybe I can share now mine with the final closing slide that you should be able to see after the agenda. There we go. So this is a summary slide. I'd like to thank our speakers for very interesting talks and great discussion at the end. And thank you to all participants for listening and for taking part in our interactive sessions. As I mentioned at the beginning, the recording of this webinar will be made available to all the registered participants. And there is just one last thing from us. As part of the ConcenSus project, we have launched a survey on the state of the art of measurements for particle number, concentration, density, and refractive index. This may not be the key measurements that the community needs right now, but they are definitely increasing in importance, especially the density and refractive index as input parameters for number concentration measurements. That is one of the top parameters that community would like to characterize. So please help us to direct our project by answering questions in this survey. It should not take longer than 15 minutes. You can just scan the QR codes with your mobile phones, and it will take you there. If you have any questions, follow up from this webinar, please contact myself or Dan directly. You can see our emails at the bottom of the screen. And thank you again for your time today and for joining this webinar. Dan, have you got any final?
I have started clapping the hands for ourselves. Yeah, thank you. I have a good impression and good discussions. We have to stop. I think it is need for more discussions in future webinars and workshops. Please, you can join and stay in contact with us. And maybe I have only 2-3 final notes here. I think some people, some attendees here are not really convinced that the transportation or particularly when we are talking about short-living materials, reference materials, to think how to combine this to include the transportation. Also, many greetings to Australia, particularly when we transport samples from Europe to New Zealand and back and forth. It is a real issue. We have also seen that we are fully in the developments of reference materials with a higher degree of complexity. We are no more talking about monodispersed nanoparticles, only gold. Meanwhile, we have definitely more complex sizes, shapes, polydispersity, also chemistry, and the problems, the associated problems, okay, the uncertainties at the end are larger. But we have to learn to live with this, to reduce or to increase the uncertainties and to talk about research-grade reference materials. The colleagues from US have started with this. Many greetings to Jeff Fagan. I have seen you in the participants here. We are talking in the last time again and again about this, and talking a very nice conclusion, Andreas, from you, talking about also fair digitalization of data and where the automation and particularly the digitalization can help us, and putting robotic at work and automation there where requests on demand is necessary. We stay in contact. We will try to put all the results, the good input. Thank you so much from you in the polls and from the chat and from our direct questions. And we will try to publish these results to come back to you in a sort of white paper or maybe publication. We will see, dependent on the quality of the results and analyzing them in peace. And thank you. A final thank you for participation, and stay in contact with us for the next events of the project ConcenSus. Have a good afternoon, evening.
Thank you. Goodbye.
Thank you.
Take care.